Hey, Alex. Good morning. Hello, Amina, Louisa, and Alicia. Today's the 11th. And hello, Lola, Feeney, Penelope, and Oscar. Just writing down everybody who's here. You can write down what's on the board if you want. That's what we're going to work on first, folks, if you can see that. Okay, let's see if we get some others showing up. I got 8 of you. That's a good start. And we're doing some PE diagrams so you can review your notes from last week and write these 4. Write down the diagrams A, B, C, and D. Try and write them just as I have them up here, and we're going to try and answer. You're going to try and answer the 4 questions. Good, and I also got Bella and Errol. Dynamite. 5 to go. Good, and I got a couple more too. I got Antonine. If you're just joining us, please write this down. We're going to work on that first today. And there's Chelsea as well. 3 to go. Aiden is here as well. Thank you. Okay, I'll put that aside. Just 2 that I'm waiting for, but I know Ellie can't make it. And we'll see if Anne-Sophie makes it. Everybody else is here. So, my people, good morning. Here we go. Remember these guys? So, potential energy on the left side of the reactants, on the right side of the products. And we got a little bump at the height of the bump. The height of the bump is called the energy. What's the height of the bump for? Going from there up to the very top. Look back on your notes, please. What's that type of energy called? We'll need it again later today. What type of energy is that? Look back on your notes. From where the reactants are to the top of this little hill. There, I got a bunch of them. Thank you, Bella and others. Activation is the right word. Activation energy. Super. Yeah. The energy needed to break up bonds, right? So here's my reactant. Boom. Break the bonds. Get them all broken up at the top. And then make new bonds. That's chemistry, right? Breaking bonds, making bonds. Essentially, we're breaking them here and making them here on the way down. Okay, so thank you all. Yes, let's go ahead and answer some questions about these. So write them exactly as I have them. Try and keep the bumps the same. And while you're writing, you can also maybe answer one that's not real hard. So which are endothermic? And I'll read the other questions too. 2 says put them in order, the fastest to slowest. And I mean the forward reactions. 3 says put them in order, fastest to slowest for the reverse reactions. Worry about it when you get there, not now. And 4, which product would be the most stable? I'll let you guess at that when we get that far. So try and answer A, B, C, D. You don't even have to write the questions down. You can just put your answers and then put what it represents next to your answer. You know what I mean? Like or endo or whatever, or exo. And you can just write for 2, fastest to slowest, or fastest to slowest reverse. So make your notes quick. Last one, just write stable. Okie dokie, let's see, I'm going to randomly pick somebody. Oscar, you're my random pick. So Oscar, do you have a guess for 1? Which are endothermic? Which letters, Oscar? I'll give you a moment to respond. B and C is right. And Amina, yes, I know you had that same comment last week, which is fine, but you know what? It's the overall process that they look at, Amina. So if I start with with we want something that gains energy. If I start here and end up at a higher spot, then overall the process is endothermic. That's what the question really is about. And then here again, lower to higher. So Oscar's right, as are most of you. Thank you for answering. And yes, gotcha. Okay. We all right? Okay, yeah. And the others must be exo. So let's see. Yeah, exo. So that's giving off energy because it's so much lower here where the products are than the reactants. And this one's the same way. The products are much lower than the reactants. So it's exothermic. Okay, you're all warmed up. I love it. Go ahead and stretch your brains. So for the next one, take a guess. Yes, if it's wrong, you'll just fix your guess. Don't worry about it. I want you to put them in order, the fastest to the slowest. So what would you guess? Look at the 4 diagrams, which would be the fastest, which would be the slowest. Go ahead and put them in order and we'll take somebody's guess. Just write something down. Okay, I'm going to randomly pick somebody for the fastest one. So how about Lola? Lola, what would you guess is the fastest one of A, B, C, or D? I guess C. No, it's not C. Which is the fastest one? Think of the easiest one to accomplish. One should stand out. The easiest one to accomplish. Ooh, I got everything but the right answer. All right. Okay, I'll start you off. A is the quickest, definitely. Okay, so you put them in order then, the rest of them, and we'll talk about it when you're done. A is definitely the fastest. Put the rest in order. Good, and I'm going to go to Lola's answer because it looks pretty darn good. So she says the second fastest is D. She's right. And it has to do with the height of the activation energy hill, doesn't it? Look at that. A little bit higher activation energy. Then she says C, a little bit higher yet, and very much the slowest is going to be B. So you can write down here something you learned if you didn't know it. Okay, so the lower the activation energy, EA, we agreed is going to be our abbreviation for that. Generally, the faster the reaction. So low activation energy, higher, higher, and really high. So A, D, C, B. Okay, I hope you've gone on to C. So let's do the reverse reaction. So now what does that mean? Reverse. You're starting at the product side and you're going back to the reactant side. What we're going to learn in book 2 is most reactions go both ways, as it turns out, not just forward. So if you're going reverse, put them in order as well. And I'm going to go to Aiden for this one. He's got a guess already, and as does Amina. And your guesses both are the same and look good. So, so Aiden and Amina, my two A's. Here we go. They said B is the fastest, and they're right because it's got the lowest activation energy if we're going backwards. So we got B. And what'd you two say next? You said D and C. Oops, maybe I'm looking at your old answer. Yep, C, right? C. So low activation, a little bit higher with C, a little bit higher with A, and the slowest one from the product side going backwards would definitely be D. That's a very high activation energy for the reverse reaction. Yeah, I can feel the gears are turning, and thank you for that this morning. I know it's not easy to get up. So, pardon me. The last one, number 4. Which product would be the most stable? Ooh, I put this in the wrong answer spot. Sorry. That's here. Okay, so most stable. So which would be the most stable and why? Which would be the most stable? A, B, C, or D? Just one of them. Good. Antonine, Oscar, and Errol. I got a lot of students whose names start with vowels. And you're all right. It's D. So the most stable, I'll put it down here, is D. Why might that be? Why might that be? Antonine says because it's got the lowest potential energy what a product is, I'm assuming. Yes, and something else, Antonine, on the product side. Yes, it has the lowest PE, but there's something else about it as well. Hint, look at question 3. Why is D the most stable? Look at question 3. No, it's not really staying constant, Bella. Flat line? No, they all got a flat line. So no, that's not doesn't really matter. It loses the most energy. Yes. Another way to say that, Errol. Yeah, Amina, it's slowest for the reverse reaction. Okay, that's really what it's about. So think about A versus no, think about B and D. So pretend you're a molecule here. Man, I could heat you up and bounce you around, and you're not going to get over this activation energy hill going backwards very easily. That's a lot of energy. But what if you're here? I bounce you around, and quite often I get you bounced around enough so you break your bonds and you go backwards to form the reactants again. This happens a lot in chemistry. So, yeah, that would be the least stable, would be B. The most stable would be D. So I'll say D, which has the highest activation energy, E sub A, for the reverse reaction. That's what it's about. Yeah, you might say, Mr. Weiss, this is kind of a weird thing. Who cares about stability? Well, I'm going to tell you why we're talking about this now. Let's see if you got any questions first. Yeah, Oscar had it. Yeah, exactly. Good. There's a lot of chemicals that chemical factories make and pharmacy companies make, pharmaceutical companies. So medicines, industrial chemicals. If you make something, oftentimes it's very unstable and it will go back to what it began with. And if you're a chemical or pharmaceutical company, you don't want that to happen. You went to all this trouble to create your product. And what that means is if it's fairly unstable, you've got to find a way to get it out of there and isolate it or cool it down or something before it reacts and goes back to the things it started with. Okay, let me give you two cases in point. Metals. If I have metals, some metals oxidize easily. I don't want them to sit there and react with the air and go backwards to essentially rust or oxidize again to what they started with. You want a pure metal to sell to make tin cans or cars or whatever with. The other one, oh, it's just flipped out of my mind. I can't think of it. But I hope you get the idea. Stability is important. Important. And if you make a product, you don't want it to really go back. Oh, I thought of another one too. Hydrogen peroxide. So H2O2 can easily go back to H2O plus O2 gas. See, is that balanced? No. So how do I balance it? Probably I do this. I think that's balanced now. By the way, this is aqueous. Here, let's talk about this. Hydrogen peroxide. It's used as a what? A disinfectant? Disinfectant. And it's used to dye hair or bleach hair. So if you bleached your hair, you might have used this stuff. When I was little, we had a bottle of it in our bathroom cabinet, right? It was a quick antiseptic if we had got a cut or something, okay? It's unstable. So the bottle is sold with a loose lid. Why? So when you buy the stuff, whether it's here in Germany or in the States, you get a bottle of it and it's aqueous, okay? So this reaction happens all the time. If I heat it up, it happens more. If I add a catalyst, we'll talk about that later today, it happens more. But yeah, so why do they sell it with a loose lid? Can you guess that? Not a tight lid, but a fairly loose lid. It doesn't fall off, but it has to be loose. Why? Why don't you want a tight lid on this stuff that you buy? Why a loose lid? Yes, good. Okay, Antonine's got it. Ding, 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 ding. So you don't want the pressure to build up. Yeah, from what gas? What gas is forming, folks? Exactly. Right. Exactly, Alicia. The gas could build up. What gas? O2. You don't want that stuff to build up. If you do, it's called a bomb, not a bottle. Okay. 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 So O2 gas pressure. That's why you want it loose. I'll say the O2 gas must escape. Otherwise, you got a bomb. That's not what you want. Cool, huh? Okay. I think everybody's all warmed up. What time we got? 8:51. We're going to go to 9:30 today. I'm going to take a pause now before we go on. And am I going to do that? No, I'm not. I'm going to continue on for another 10, 15 minutes, and then we're going to pause and see what questions you got. Okay? But I'm going to do a little more new stuff because you're all warmed up and you all got the right idea now. Yes, thank you. Good. Okay, so away we go. Yippee skippy. Okay, let's see in my book. Where did I put that? Oh, I left it at school. That's right. Just making sure we picked up everything in chapter or section 1.6. And I didn't get every detail, but she added numbers to it, but you'll be able to do that now, I think, rather well. Okay, except we need to talk about catalyst. Okay, so here we go. I'm at page 71, by the way, just for grins. So page 71 is our first mentioning of catalyst. Some of you probably had this in another class, especially if you had Miss Galloway or somebody. Catalysts are chemicals that the reaction rate but are not Let's see if anybody can fill in the blanks if you've had that before. Thank you, Feeny. She's got one already. So catalysts increase the reaction rate. They make a reaction happen faster. If I add I minus to hydrogen peroxide, the O2 just like flies out. We'll do that maybe in the spring. Oh, I hate that. Sorry, losing my markers. Increase the rate of chemical reaction. Yeah, not fully consumed. Good. You're close, Amina. They're not consumed at all. So, but are not, I can say themselves, consumed in the reaction. I think we already did this, didn't we? Did I already give you? Yeah, we did this already. Didn't we do this with formic acid and the breakdown of formic acid with H plus? Did I do that with you already? The stuff that's in ants, amy's azoita? Yes, yes, no, no, or is that one of my other groups? We did do that. Okay, so we had an example. We had an example already of a catalyst, and it was H plus when we added it to aminozoida, and it broke the stuff down easier. But at the end of the day, if you remember, the H plus was given off again, so we know it's a catalyst. So a catalyst is themselves not consumed, okay? That's really important. If it's consumed, it's not a catalyst, okay? It's got to come free again at the end of the reaction. Huge. Let's do another potential energy diagram. Okay, let's make it like this. I don't know. Mm, mm. Let's let that be without a catalyst. Mm-hmm. Mm-hmm. What do you think it'd look like with a catalyst? Okay, thank you, Anne-Sophie. Okay, so what do you think folks would look like with a catalyst? Type in your answer, and then we'll draw it together. So there's a endothermic reaction, slightly endothermic, and with a catalyst, how will the picture change? Exactly, good. Yep, good. Yeah, very good, all of it. So let's do it. So a lower peak is what a lot of you said. So a lower activation. Watch this. It's like a cute little tunnel. Beep, 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 beep. Isn't that cool? So I could say with a catalyst, it's got a lower. With a catalyst, let's see if somebody said it anyway. Yeah, Alicia did. It's got a lower activation energy. I'll abbreviate that. Nice. Okay. So just as kind of review, because I think I didn't say it this way last time, okay? Activation energy when molecules achieve this energy, they are colliding hard enough to react. So it's about collisions. I wanted to say that last time and I forgot. So when molecules, that's supposed to be a M, when molecules achieve this energy, they collide hard enough to react. To react. So the cool thing about catalysts is they can collide, right? Here's the regular one, but here's this one. They can collide with a lot less force, can't they? And still break apart, okay? And then make new molecules here on the other side. Good. Let's pause and see if you have any questions about that point. Yeah, catalysts really save a lot of time and often save money for companies. As a chemist, one job chemists have is looking for catalysts to make reactions happen quicker or make medicines happen quicker, right? Wouldn't you love a catalyst right now that would make producing, manufacturing the vaccine for corona faster, right? That would be a very practical catalyst to have right now at a pharmaceutical factory. So catalysts are often good. I'm looking here while you think about any questions you might have, but I think we're pretty good. I think we're very good. Huge. Okay, so we're going to go on to section 1.7, just so you know what we're doing. And what time is it? No, we're not. It's 9 o'clock. So I promised myself that once we got this far, I would pause and take some questions from you. Okay, so we're up to 1.7, which means you can do pretty much all of chapter 1 now. Hopefully you got it done. I'm going to send you chapter 2 rather soon. I'm going to assign a AP classroom quiz again this week. And yeah, hopefully chapter 1 is nearing completion. Let's figure out which ones we'd like to ask about now. Okay, so do you have some chapter 1 questions that you're working on? When is chapter 1 due? With Corona and everything, I don't think we put a due date on it. Let's make it due. Oh man, how about Thursday? So chapter 1 due Thursday. And I'll give you chapter 2 already if you're already done with it. I'll send that out to you today, the chapter 2. Okay? All right, so hammer away at that. We'll take questions on Wednesday and Thursday that you still may have on it. By the way, if our questions are really long and really involving a lot of numbers, I'll probably cut time and answer the rest of it via our group chat or just individual emails. You have okay, you have Louisa, you guys have chapter 2 already? That would be good. You want us to send you pics of our work? No, I don't, Anne-Sophie, because I don't want to have you take pictures of your whole flippin' chapter 1 book. I just don't want to do it. Now, we're going to wait until I see you live someday, and then I'm going to have to grade some chapters, won't I? But I don't think we do. Okay, so great. So you have chapter 2 already. I'll assign that chapter 2 officially. Oscar, do you have chapter 2 as well? Did you get that somehow from me? And anyone else who may not have been there? When is the online quiz due? I'll let me make it first, Errol, and then I'll try and put a reasonable date for the online quiz. No, not yet. Okay, I will send that to you. Other than Oscar, does everyone else have chapter 2? I think you do, but let me know now if you don't, and I can send it to you if you do not. I'll send that to Oscar today. Okay, all right. Okay, I got a suggestion from Bella already. So page 21, number 3. Thank you, Bella. Here we go. I'm going to erase some of this now. In fact, all of this. And we'll see if we can answer some questions. Okay, so page 21, number 3 says, so it's part of this activity. Calculate the average rate in milliliters H2 per minute. The average for each trial. Use the time required to collect the maximum amount of hydrogen gas formed. For example, the time for trial 2 would be 90 seconds. Yeah, right. Place the rates on graphed lines. Calculate the average rate for each trial. Place the rates on the graphed lines. Okay. All right. So, okay. Thanks, Bella. Let's see. Let's just do one and see if you did it the same way and see if everybody else did. Okay. So for trial one, we had a concentration, by the way, of what, 1 molar. Use the following graph to guide all 4 sets of data. Okay, I'm going to look back at the graph, make sure I know what I'm doing. Okay, use the following grid to graph all 4 sets of data. Okay, if it's sets of data, then I think we need to have several values for each trial. Vary each color. Okay, so now I think I know what I'm doing. Okay, so trial one. Let's go for the first 30 seconds. So we're going to go for 30 seconds. Oh, sorry. Oh, man, it's milliliters of H2 per minute. That's kind of great. Okay, so 30 seconds would be half a minute, right, gang? So the first one we have is what? 12 milliliters. Everybody look on page 20, right? Page 20 is the graph. So I'm looking at trial one. Everybody there? So I got 12 milliliters of H2 divided by 30 seconds, all right? Half a minute. Well, that divided by half would be 24, right? So 24 milliliters per minute. Let's do the next one. Okay, from 12 to 19. From 12 to 19, Bella, we got another half minute. But from 12 to 19 is 7 milliliters of H2 formed. And so it's per half minute. So now I got 14 milliliters per minute. My other class folks, are you getting the same answers that I got so far for your trial one? Are you getting the same thing I am? I hope so, because I hope I'm doing it correctly. Then for the next one, we got only 5 of them. 5 milliliters H2 going to 90 seconds, so another half minute has gone by. So now I've got 10 milliliters per minute. Look at that, my rate keeps going down. Crazy, huh? And I think I'll let you do the rest. Now let's see if I can. Do I calculate the slope? I don't know, Bella, unless they ask you to calculate the slope. Let's see. Place the rates on the graph lines. Okay, the slope keeps changing, so I don't think you're gonna. Well, no, I take that back. I don't know. Plot them up, but it doesn't say to. Let's see. Calculate the average rate, and then use the times required to collect the maximum amount of hydrogen gas formed. Place the rates on the graph lines. The only way to get the rates, these are going to be, this is, I think, first order. Maybe I shouldn't tell you that. But I think it's first order. So if I just have the reaction rate, I can't get the slope very well there. In a sense, the rate is changing the whole time. So no, I don't think you need to find the slope there. Okay, others, have you done this? Are you getting the same thing I am? Yes, yes, no, no. Please tell me someone's done this already. It's only page 20. Did you get these same numbers that I did? 24, 14, 10. I'm not going to do all of them, but that's the way to do it. All right, then I think that's enough to have you continue on your way. So it's a lot of math. It's a lot of graphing. And yeah, you'll have one for each of the 4. So you have 4 lines on your graph. Okay. And this one I'm not quite done with. There'd be a couple more, and you'd graph those maybe in one color and so on. Yeah? Okay. Folks, you need to get going. If you're really only on chapter on page 20, that's not so hot. So give yourselves a kick in the patootie and start working your chemistry. So Wednesday I can take questions, hopefully a little later in the chapter. Okay, other questions from you in chapter 1? And while you're thinking, I'll make a little board space. Any others in chapter 1? Are you still there? Yeah, theoretically, you guys are still there. All right, we're going to go on if you don't have any, but I'd rather have you ask if you have some. Nope. Okay, then we're going to go on. So we're going to go back and talk about types of catalyst. So I'm at page 84. Types of catalyst. The first type is called a carrier catalyst. Or, unfortunately, it's got two different names, each type. It's a carrier catalyst or homogeneous. You've all had homogenized milk, right? It's the same throughout, right? Homo means the same. So homo is the same phase. So homo here means same phase as the chemicals in the reaction. Okay, so carrier catalyst or homogeneous catalyst, I think that's what Cheryl uses. They do their job. Remember, they speed up reactions. They do that job as they're carried along by the chemicals. And the example, folks, that we have is the H plus to break down formic acid. So we had that in your notes already. Right? The ants contain formic acid. And the H plus is carried along, does its little job, and then at the end of it, it's released again. And it's the same phase, it's aqueous, just like the stuff it's working on in the acid. Okay? All right, so that's a carrier catalyst. So essentially, you've had that kind already. The other kind is called a contact catalyst. Or a catalyst. So what would the other kind be called, maybe? Type in, fill in the blank for me. Let's see if you guys are still out there. Hey, somebody's there. Good. Amina's there. And so is Bella. Good. So that's correct. So the opposite of homo would be heterogeneous. So different phase. And as an example, I want to give you the most common heterogeneous catalyst ever. And the most common one ever is found in regular cars. Not in electric cars, but in gasoline-powered engine cars, which is most of the cars on the road. So an example, and Cheryl has a good picture on page 85. example of a contact catalyst is a catalytic converter. In a car. Or if you want the German word, Katalysator. Katalysator. Well, what does this thing do? I can't draw it as well as Cheryl, but I'm just going to roughly say it cleans your exhaust. And it's the most expensive piece on the car. You'll soon see why. So it's more or less a honeycomb thing, but I can't draw that. So I'm just going to draw some chicken wire instead. So here's your exhaust coming in. And it goes through this honeycomb. And we'll just draw some wires here, okay? So what comes in is stuff that is not very clean gas-wise, which is stuff like, well, I know what I'm going to put. Does she put anything? Okay, it's carbon monoxide, which is poisonous. And another one that comes in is NO2, which is the brown stuff in smog. Okay, these are nonmetals, right? Carbon and oxygen are both nonmetals. Nitrogen and oxygen are both nonmetals. So what they're attracted to are metals because they want the electrons in a metal. So what this stuff is, this grid, this honeycomb here, is coated with something that has free moving electrons, coated with platinum. And platinum, you guys may know, is super expensive. Could be another, but platinum's the most effective. Okay, I'm going to stop writing small and write down here how this works. What really goes on is this. The CO, for example, lands on the platinum and says, oh, look, here, we'll do a little up close thing. So here's a wire with platinum. Okay, by the way, it's just coated with platinum. It's not pure platinum, but it's the most expensive part on the car because of that platinum coating. So in comes the CO. And the CO has a triple bond. Did you know that? So it's got a little plus, a little minus here. And the thing lands because C and O both want the free moving electrons. And what happens is once it lands here, both the C and the O, they kind of like look down. Okay. Well, they don't really look anyway. They don't have eyes. Okay. But they're attracted to the electrons in the platinum. So this weakens the bond. So CO lands on platinum and the bond, the C triple bond O bond weakens. And then somebody comes in and hits them. So that bond's weak, and just by luck, what hits them? But somebody called O2. Slam-o-bama. Boom! And we make something coming out the other side called CO2. Yeah, it's not great for the atmosphere, but at least it's not poisonous like carbon monoxide. So that's what they mean by cleaning up the stuff. Similar thing happens with NO2. I get N2 coming out the other side and probably some other O2s and stuff. So this catalyst weakens the bond. And then when it's done, it releases again and goes off and becomes CO2. So the platinum is not used up. So it's a true contact catalyst. And notice they come in contact with each other. That's why it's called a contact catalyst. And they're different phases. This is a gas. And the platinum is a solid. So they are heterogeneous, right? Heterogeneous And again, the platinum's not used up, so it is a true catalyst, can be used over and over and over. And there's a better picture on page 85 in Cheryl's book of that. But that's how it works. That's the guts of how it works, okay? The bonds get weakened. So essentially, the activation energy is lowered, just like all of you guessed with the little tunnel through the activation energy hill, right? It's lowered. Beautiful. Beautiful. That's enough of that. No way. Okay, I appear to be done with chapter 1, but I think there's one other thing I didn't get to. And it's a big thing. Yeah, okay, got it. All right. The last thing in chapter 1, holy moly. So I'm up to page 85. And I'll show you an example on Wednesday. It's called a reaction mechanism. How are we doing on time? We still got a few minutes. Okay, so what's a reaction mechanism? It's the series of little steps that result in an overall reaction. You and I did this earlier in the year, but it's been a while. I like to do an analogy first, okay, before we do a chemical. And then I'll do another chemical next time when I see you Wednesday. Okay, let's pick somebody. Let's pick, I don't know, let's pick Chelsea. Chelsea, you still out there? And if you are Chelsea, do you like oranges? I guarantee this won't hurt you. Do you like oranges? Oh, good. And she says yes. Okay, good. All right, so here's the game. We're going to say that that Chelsea loves oranges. So she is here, and she is. I don't want to draw this. So she's here. She's eating the oranges. Okay, and she eats them really. Thank you, Chelsea. So oranges are great. So she's eating the oranges. In fact, she eats them pretty quick, so that by the time a little bit of time has gone by, the oranges in the bag of oranges are gone. And her family, someone from her family, has to go out and buy more oranges. So they go out, they drive all the way to the store, and they get the bag of the oranges, and then they stand in line and they pay at the casa, Then they drive all the way back and they give her the oranges. Well, then she eats the oranges and they're pretty much gone. And then, of course, they got to get in the car. They got to go drive back to the store. They got to go find some oranges. Then they got to go wait in line. They got to pay. They got to load the oranges and get in the car and drive all the way back. Notice that this process takes a while, doesn't it? and and if I want to make this process happen faster so that Chelsea can be enabled to eat a whole lot of oranges in a short period of time and increase her rate of eating oranges, could I just have her eat them faster? Would that speed up the process? So to speed up the overall process, will it help if Chelsea just eats the oranges faster? Yes, yes, no, no. To speed up the overall process, will it help if Chelsea just eats the oranges faster? Right, Alex. Alex says she will soon run out of oranges. So that's not going to be very helpful. So instead, what process could I maybe speed up that would really matter? What step could I speed up that would really matter, that would really help this process to get Chelsea more oranges? What step could I speed up? Okay, the buying the oranges. Okay, the spending to buy. Oh, I got lots of good answers. More packs of oranges. Good. Let the car trip. Essentially, let's take Bella's answer. Getting the oranges, the car trip. Right. Lola and Bella. So, really, I want to speed up that car trip because that is, folks, that's a slower portion of the process. She can eat oranges as fast as she wants, but you know what? It's not helping that much or really at all to speed up the process. I still got to wait for somebody to drive out there and get them and come on back. Well, why am I telling you all this? Because as it turns out, even though there's lots of steps in a reaction, to speed up the overall reaction, I need to speed up the slowest step. The slowest step has a special name in chemistry. You might have heard of it in other class. It's called the rate determining step. And the example, just to tweak your memory when you actually get there, is the trip to the store to buy oranges. That would be our rate determining step for Chelsea's reaction. Chelsea's reaction, eating oranges. Okay? So when a scientist is interested in making a process happen faster, and I'll be honest, what this is really about a lot of the time is money. I want to make something faster, whether it's a vaccine for the world or whether it's a product that I want to sell, I want to make it faster chemically. To do that, I want to concentrate on the slowest step, the rate determining step. If I can speed up that one, I can speed up the overall rate. Okay? So speeding this up speeds overall rate. Okay? So in Chelsea's case, maybe it could be, I don't know, maybe a conveyor belt, right? Directly from the grocery store to her home, and they just pile on oranges all day long and keep her, going with oranges the whole time. Wouldn't that be great? No problem, right? Yeah. So I'd speed up that step for sure. Good. Okay, I'm going to stop there now because that's a good place to stop. See if you have any questions. This is a hypothetical problem. Yes, it is a hypothetical problem. But the real chemicals are not hypothetical, especially if I want to make something fast. I want to try and speed up the process of making it or manufacture it quicker, like the COVID vaccine. Okay, a good real world example right now. Good. I'll have another example or two of chemicals for reaction mechanisms for you on Wednesday, but essentially we're done with chapter 1. So I will officially assign you chapter 2, and we'll pick a reasonable due date, and I'll get the quiz together today and send it to you as well through Google Classroom. No, through AP Classroom. And so if you could do it all at once, I'm not sure what it is, but I could speed up the one step. Once I speed up that one step, that speeds up the overall process. Now, here's the thought too. There are chemical reactions where I've sped up one step so much that another step becomes the rate determining step. You know what I'm saying? So it's one step, but that may change if I find a way to speed up the one step. Then maybe another step it ends up being the slower one after that. So it depends on the process. That's correct, Oscar. The quiz will be on chapter 8 in book 1, which is on the gas laws and stuff. Okay, and I'll make that really clear when I assign it to you. Yeah, exactly. That could be a way too, Anne Sophie. Right. Yeah, exactly. Good. Thank you all for participating so much. We'll see you on Wednesday, and I'll be in touch sending you messages about what's due when. I'll try and make it reasonable. Um, Come to any last minute questions on chapter 1 to me on Wednesday or Thursday. We'll clean those up, and then we'll be ready to start chapter 2. Okay? Thanks, everybody. Have a good week. Bye bye.